Okay, so we're going to look at problem 3.6 in chapter 3, dealing with a simply supported beam. The beam has two reactions. The reaction A, which is a pin, so it's modeled with two reactions. So I'm going to just arbitrarily say this goes up and this goes to the right. I'm going to call that RAV, RAH. We have an external load, 20 kilonewtons. We have another external load of 6 kilonewtons. They're 3 meters, 3.5 meters, and 3.5 meters. The other thing we have to consider is the roller reaction. Roller can only go one direction, and in this case, it can either go up or down. So I'm just going to call it up, and this is RBV. So what we're after, this is a parallel problem. We're going to solve the three unknowns. Since it's a parallel problem, we have to use sum of forces in x, sum of forces in y, and sum of moments. So I'm going to start out with sum of forces in x. Summation of forces in x by equilibrium have to equal 0. So what that tells me is that RAH is 0. There's no resisting load any direction. So let's look at sum of forces in y. Sum of forces in y have to equal 0. So in the y direction, we have RAV up, RBV up. So we're assuming that up is positive. And then we have negative 20, negative 6. All of that is equal to 0. So what that resolves to is RAV plus RBV is equal to 26. But this doesn't tell us the distribution of A and B. So what we're going to do is resolve it with a moment. So we're going to go in and do a moment equation. Summation of moments about any point have to equal 0. And I'm going to define clockwise moments as positive. So you want to take moments where it's going to do the best result, knock out unknowns. So A would be a good place and B would be a good place. I'm going to go ahead and decide to take it at A. So we have a force times a distance. We have force, which is 20 at 3. And this is giving me a clockwise moment, so it's a positive moment. Then we have 6.5 times 6, and that's also a clockwise moment. So that's going to be a plus 6 kilonewtons times 6.5 meters. The last thing, we know that this is 10 meters across. RBV is tending to act at counterclockwise, so we're going to decide that, or counter that as a negative 10 RBV, and by equilibrium, this has to be equal to 0. So this is solvable, RBV. If we do the math on this, we'll see that this times this plus this times this should give us a negative 99 when we come across. Divide that by a negative 10. That gives us 9.9 kilonewtons. The positive result is telling me that it is acting in the direction that I indicated initially. So that's my one answer. Plugging that back in, we have RAV is equal to 26 minus 9.9, which gives us 16.1 kilonewtons. Also a positive answer, and so therefore there's our solution. So resolving everything, pretty easy. These should equal each other and are equal to the original. That's the easiest way to do that.